We are Team Bomb, and we will be discussing the fluid mechanical concepts behind the impact sprinkler. Starting with a synopsis of how the sprinkler works, at the end of this curved pipe, a hose can be attached here, allowing water to enter the system. Water flows along the internal piping of the sprinkler until it reaches the nozzle, shown here. When the water shoots out, its path is redirected by this arm. When the water hits the arm, it gets flowed to the left. With the arm out of the way, flow can now return to its initial path. The force from the water, which causes the arm to move, is dampened and absorbed by the spring, which then works to push the arm back to its original position. The resulting impact from the arm returning to its original position generates a torque sufficiently strong enough to overcome static friction and nudge it to the left, driving the sprinkler in a counterclockwise rotation.
So now we move into the piping of the sprinkler. We start with the inlet flow from the hose into the sprinkler. The sprinkler is designed to have a minimal change in area from the hose diameter, in this case a 5/8 inch inner diameter hose, in order to reduce losses so that the water has sufficient velocity and pressure to be able to move around the bend and the vertical section that comes up after the inlet. And here we also have a calculation using the volumetric flow rate typically used with a sprinkler in order to calculate the inlet velocity of the water.
The Reynolds number tells us how turbulent or laminar a flow is. Average impact sprinklers have a gauge pressure of around 30 psi and a flow rate of around 10 gallons per minute. By plugging in these values along with the properties of water in the measured dimensions, we calculate the average velocity to be around 4 meters per second. Then we calculate the Reynolds number to be around 60,000. Therefore, the flow of the water is turbulent. We can use the Colebrook equation since the fluid is not a laminar flow. Given the roughness coefficient of steel, we find the viscous dissipation factor to be 0.04. We can see that this agrees with the Moody chart. If the pipe were made out of a more rough material, or if a thicker fluid were used instead of water, then the viscous dissipation factor would increase as shown by the equations. Therefore, the velocity of the fluid decreases as well as the Reynolds number. An increase in pipe diameter would also lead to a decreased velocity due to the conservation of mass. Lastly, if there is a greater curvature, then the flow is more turbulent and there are more separations in the flow, meaning that there are greater energy losses.
Here we have a streamlined drawing on the CAD of the sprinkler. You can see that the lines are further apart near the inlet, and that is because there's a higher pressure there, and then the streamlines move around this bend and go up through the vertical section, which has a lower area. So by Bernoulli's principle, that should yield a larger velocity through the straight part. And then it goes around another bend and goes into the nozzle, which will increase the velocity even further. Therefore, the streamlines are closer. If we do not assume the flow to be inviscid, there are possible losses and separation in the bends, as shown here and here. As you can see, they curve to the outside of the bend. However, the piping has a small diameter, which should limit the formation of large separation zones and formation of vorticity and eddies here. Due to the small diameter, turning beams would also not be practical for limiting these losses.
So now we move on to the nozzle. The nozzle is shaped to minimize the losses while achieving the target velocity of the stream as it exits the sprinkler. And after exiting, the water pushes the deflector plate, which in turn pushes the sprinkler arm connected to the spring that turns the sprinkler. The nozzle also lowers the pressure of the water by constricting the diameter of the pipe to atmospheric pressure and increase the velocity through the Euler equations, which you can also see with Bernoulli's equation here because it is an incompressible flow. So all these factors impact the velocity of the stream exiting. Specifically, it is parabolically shaped to minimize vortices due to the gently sloping sides of the nozzle. The fluid flow stays as laminar as possible by ensuring that there are no sharp geometries that the fluid can get stuck on, so the boundary layers are minimized. Now, if you have a larger exit area, a smaller angle, a more viscous fluid, or a lower pressure head, these all would contribute to a lower exit velocity due to Bernoulli's equation.
For the exit, conservation of mass and Q equals UA were used to calculate the velocity of the water stream as it exits the sprinkler. We assumed no losses in the calculation of the velocity of the exit stream, which meant that U inlet times A inlet equals to U exit times A exit, which equals the volumetric flow rate. Knowing this, we decided that we needed to find values of the volumetric flow rate of the water through the hose and the area of the exit hole to calculate the velocity of the exit stream. In order to do this, we calculated the area of the exit hole using the diameter we measured and looked up the volumetric flow rate of the hose. Using these values, we calculated the exit velocity to equal 5.4864 meters per second. Once the water exits the sprinkler, we assumed that the stream was a free jet. Using this assumption, we calculated the range of the jet to be about 2 meters.
Lastly, these are the engineering models we used from Appendix A. First, we transition from lab frame of reference to object frame of reference. We use the continuum model at the nozzle and exit, the Newtonian fluid model, and the no-slip condition in the pipes. We used mean flow in the pipes in the exit. We used incompressible flow in the entire sprinkler. We used fully developed flow in the straight pipe. We used boundary layer equations in the pipes. And lastly, we used Reynolds average flow in the entire sprinkler.